Infinity, and we have two contestants who are going to tell us what is so awesome about infinity. First, we're going to have Dr. Wendt. He's going to tell us, I don't know, something.
Stuff.
And then Dr. Cline will tell us some other stuff. And then you can ask us questions. So be thinking about what questions you might have. And then at the end, we get to vote on whoever is best. That's our plan. Are we ready to get started?
Whoever gets the best debate, that's the best.
Yeah, best debate, best convincing argument about infinity.
All right. All right. So before the event, we flipped an imaginary coin, and I won. So I get to go first. My name is Ted. I'm going to be talking a little bit about infinity. Of course, you know that. That's in the advertisement. I do want to just throw out there. So we are the Carroll College Department of Everything. We represent the Department of Mathematics, Engineering, Computer Science, Computer Information Systems, Geographical Information Systems, Physics, Data Science, and stuff. So we've got loads and loads of different students, we've got loads and loads of different faculty. We're all excited to talk about this sort of thing. Tonight, Dr. Cline and I are the lucky ones who get to face off in this debate. And we're talking about infinity. Everybody has some sort of conception of infinity, but infinity is weird. And I'd like to focus on some of that weirdness as my candidate for the coolest, most mind-blowing fact about infinity. So, some things that I've heard students say about infinity. When I ask them, what is infinity? They say, infinity is endless, it's unlimited. It's 1 divided by 0. Some people say it's a direction. It's like at the far end of the number line. That's infinity. It's a really big number. Some people just like it as a sideways E. Some of the more mature students say, oh, you know, it's an abstract concept. It doesn't exist in reality. But in general, people don't know. They know, they have an idea, a concept of, yeah, I can kind of talk about, that must be infinite and that must not be. But when we want a precise definition, that tends to elude us. So we're going to take a look at infinity from the mathematical perspective. And for me, one of the simplest definitions of mathematical infinity is infinity, this sideways 8 symbol, is a quantity with the following property. For every real number x, infinity is bigger. And that's it. It's a simple definition, but there's a lot hidden in that definition. So we're going to take a look at how that simple definition breaks some of our core principles of mathematics. All right, so we're going to start from the very, very beginning. Suppose I have some stuff that I want to count. Now, as an example, I'm going to give you this, and you can talk amongst yourselves. So suppose we have things that we want to count. How might I count that? Well, we learned this pretty early on, right? We'll start with 1, and then we'll do 2, and then we'll do 3, 4, and 5. Unless we're computer scientists, and then we'll start with 0, 1, 2, 3, and 4, right? So we count them 1, 2, 3, 4, 5. No big secret. And we repeat as necessary until we run out of things. But of course, with the idea of infinity, the question happens, well, what happens if we never run out of things? Do we just keep counting? This idea of infinity as being endless would imply that no, we can't just keep counting. And yet, if I try to keep counting further, I'll always be able to. Right? So one of the things we're going to do is talk about counting without numbers. That's maybe a poor phrasing there, not counting without numbers, but determining the size of something without numbers. So suppose I have a box of red and white yellows. Wait, red and white yellows, yes. Red and white Legos. You're welcome. All right, so suppose I've got a box of red and white Legos, and I want to figure out if I have more red Legos or white Legos. Now, the counting approach would be for me to say, all right, let me sort them all out, count all the red ones, and then count all the white ones, and then compare the two numbers. And whichever number is bigger, that's the one that I have the most of. But that's doing more work than I actually need to do. In fact, all I need to do is take a red Lego, snap it to a white Lego, throw it away. Take a red Lego, snap it to a white Lego, and throw it away. And whatever I'm left with is what I must have more of. Because in doing that, I'm saying that these things are paired. And whenever I reach something that doesn't have a pair, that means I've run out of the other one. So I've determined size without assigning a number to it. And in fact, that's going to be important for us. Infinity is not a number. So when we start talking about sizes with infinity, the idea of counting things up and then comparing, well, that falls flat. So we just need to know that every white Lego has a corresponding red Lego. Okay. Now, a little bit of terminology. The approach that I'm going to take is going to be along what's called a set theoretical approach. We're going to talk about sets in a mathematical sense. And in a mathematical sense, a set is something that's got stuff. We designate it with curly braces. So the first set up there, the set ABC, it's a collection of 3 things. They're all letters. The second one, the set 2, 3, 5, 7, 11. Those are the first 5 primes. It's a collection of things. The last one there, 1, 2, 3, 4, 5, ... I can talk about a set of all the counting numbers, starting from 1, adding 1, until I get tired of writing things down. Those are all sets. And one of the questions that arises then is, when do sets have the same size? And this is the first lame definition. 2 sets have the same size if we can pair up each element in the first set with an element in the second set without reusing anything in the first set and without missing anything in the second set. Right? In other words, Legos. Right? 2 collections of Legos are the same. If I can take a Lego from each, pair them together, and I run out of them both at the same size. Now that's great from an intuitive standpoint, but from a practical standpoint, that's pretty unwieldy. So we can make it a little bit more precise. We can say 2 sets have the same number of elements if we can find a 1-to-1 correspondence between the sets. Again, the same idea. Take one from here, match them up, and everything has a pair. Now, formally, from a mathematical perspective, we do this one. We say 2 sets, A and B, have the same cardinality. We have to use a fancy word for it because we're mathematicians, and this is special stuff. So they have the same cardinality. If there exists a function, the notation there says a function f that takes elements from the first set A and pairs them or matches them with a corresponding element in the set B. And this function has to be both 1-to-1 and on. And what that means is, from the mathematical sense, 1-to-1 says if I pick something in the first set and map it to something in the second set, nothing else maps to that thing. There's only one thing that goes to that B element. Onto says if I pick something in B, something's going to map to it. In other words, everything maps to one and only one element, and nothing gets missed. Okay. So these are 3 ways of saying the same thing. The third way is the way mathematicians formalize it, so that we can compare things when intuition fails. All right. So I'm going to state some obvious facts. I say they're obvious. I hope they truly are. Okay. So the first obvious statement about finite sets is the size of a set is the same as its size. A set is the same size as itself. Now what that means is there exists a 1-to-1 and onto function that takes elements from the set to itself so that everything maps to something and nothing gets mapped to us. Right. So yes, obvious. For finite sets, a proper subset of a set is smaller than the set itself. Now, a proper subset is made when I take stuff from the set, but I don't take all of it. So for instance, if I go back a couple slides, here we go. The set ABC, if I just take the set AB, that's a subset of the first set. And you know what? That's smaller. It's got 2 elements. The full set had 3. The set 2, 3, 5, 7, 11, That's a full set. The set 2, 3, 5, that's a subset. That's smaller than a subset. If I take a subset of a finite set, but don't take everything, it's smaller. Right. Now, if you walk out of the presentation right now, you'll think, wow, what an idiot. I don't promise that will change by the end. All right. If there's a map from A to B that assigns every element of A to something in B, but there's stuff left over in B, then A has to be smaller than B. So if I use up everything in this set, map everything over here without duplicating, but there's still stuff left, well, that means that this set must have been bigger in the first place. And similarly, if I have a map from A to B that hits everything over here, but I have to duplicate things, well, that means A must have been bigger than B. Again, this is something we can look at. I hope these are relatively apparent facts. I'm going to stop short of giving a formal mathematical proof. But infinity is weird. And for my first point of evidence that infinity is being weird, imagine two farmers that plant seeds every day. We'll call them Farmer A and Farmer B to protect their anonymity. On the first day, they both plant 5 seeds. But now, imagine there are hungry crows. And each day, a hungry crow eats one of the seeds the farmer has planted. All right? You have no idea how long that took. All right, and on day 2, the farmer planted 5 more seeds and the crows come and eat more. But look at the pattern of how they're eating. The crow that's eating farmer 1's crop is always eating the oldest seed that was planted. But the crow that's eating from farmer 2's crop, from farmer B's crop, is eating the most recent seed, the newest seed. And on day 3, again, it is super sad how long that took. And you see the pattern. Now, after day 1, both farmers will have planted 5 seeds, and both crows will have eaten 1 seed. And at the end of the day, both farmers will have 4 seeds. After day 2, both farmers will have planted 10 seeds. Each crow will have eaten 2 seeds, and both farmers will have 8 seeds left. And so on to the end of day 3 and day 4. But what if we're allowed to continue this infinitely? What happens if this continues endlessly? Each farmer plants the same number of seeds. They each plant infinitely many seeds. Each crow eats the same number of seeds. But all of farmer 1's seeds will be gone. There's no seed that farmer 1 plants that a crow won't eventually eat. So definitively, infinity minus infinity is 0. Gasp. Thanks. But the same number of seeds planted, the same number of seeds eaten, and farmer B has infinitely many seeds left. So infinity minus infinity must be infinity. In fact, depending on how we tell these crows how to eat things, we can have any number of seeds remaining. It could be that infinity minus infinity is 7. Sometimes infinity minus infinity is 432. Sometimes infinity minus infinity is infinity. Sometimes infinity minus infinity is 0. And if we extend it, sometimes infinity minus infinity could be any real number. Now, we're told that infinity minus infinity is undefined. And I would argue that it's not so much that it's undefined as that it's over-defined. It could be any real number. There's not enough to know. We need to be careful with infinity. So, exhibit B, infinity is weird. Imagine a farmer again. Okay. Now, this farmer has already toiled for infinity, and is probably taking a nap right now. Planted infinitely many seeds. Now this time instead of crows. What do you imagine dragons? Dragons are greedier than crows. But imagine infinitely many speaking dragons. All right, now first things first. I'm gonna say all the things inside my head. These dragons, they've been fired up, and tired with the things that say, oh. I have infinitely many dragons, I have infinitely many seeds. And of course, the dragons are going to want to take as many seeds as they can for themselves. So how can I take this infinitely many seeds and split it out amongst the dragons? What do we think? Say it again.
Infinity over number of dragons.
Infinity over number of dragons. Well, there's infinitely many dragons.
Infinity over infinity.
Infinity over infinity. And infinity over infinity equals?
Infinity.
It's over 5.
0, 1, 2, 3, 4, 5.
So let's think about it. Depending on the nature of the dragons and the nature of the seeds, there are some possibilities. It's possible each dragon just decides to take one. Infinite many seeds, infinity dragons. Nice, everybody just takes one. Plays nicely. So infinity divided by infinity could be 1. But because I have infinitely many, I could say, hey, the first dragon is going to take the first 7 seeds, and the next dragon is going to take the next 7 seeds, and the next dragon is going to take the next 7 seeds after that. And in that sense, I never run out of seeds, I never run out of dragons. Each dragon gets 7 seeds. So infinity divided by infinity is 7. Now, it is possible that each dragon might get infinitely many seeds. Now you have to be a little bit clever on how you do this. So I could say, just as an example, let's have the first dragon take all the even number of seeds. Let's have the second dragon take all the seeds whose smallest prime factor is 3. Now those are going to be some seeds that haven't been taken. Let's have the next dragon take all the remaining seeds whose smallest prime factor is 5. There's still infinitely many of those. And let's have the next dragon take all the seeds whose smallest prime factor number is 7. There's still infinitely many of those. I'll never run out of primes. Every dragon will be able to get infinitely many. Now there's another possibility here too. Actually, there's 2 more possibilities. You're going to talk about one of the things that might happen, but I'm going to steal some of your thunder.
Oh.
See what I did there? Yeah. Yeah, see how I put that in? It's a theme. Everybody wants to be my enemy. All right. It's possible that there are so many dragons, that the infinitely many dragons are enough to overwhelm the infinitely many defenseless seeds, and effectively all the dragons get almost no seeds. Almost all dragons. And I say almost all in the precisest of mathematical definition. So infinity divided by infinity could be 0. Okay. Now, exhibit C, this is one that I think if you've taken some algebra courses and some graphing things, you've seen something like this. I'm talking about open intervals on the real line. So we've got the number line there. And we've got the simple question. Which interval is bigger? The interval containing all the real numbers between 0 and 1? Or the interval containing all the real numbers between 0 and 2? Thanks, Stu. All right. Now, if we just take this at face value, the interval from 0 to 1, that's 1 unit long. And the interval from 0 to 2, that's 2 units long. And 2 is bigger than 1. So we might say that, yeah, the second one is bigger, but really it's a bad question. It depends on, well, what do you mean by bigger? Because in one sense, the second interval is twice as long as the first, but mathematically, they have exactly the same amount of numbers in them. Every number in the first interval corresponds distinctly and uniquely to a number in the second interval. There are precisely as many real numbers between 0 and 1 as there are between 0 and 2. The same as there are between 0 and 10. The same as there are real numbers, period. If you take all the real numbers from negative infinity to infinity, there are exactly the same amount as there are in the interval 0 to 1. Now, mathematically, we can do this through a correspondence. This here is a graph y equals 2x. And this tells you exactly how to calculate which number in the interval 0 to 1 corresponds to which number in the interval 0 to 2. Okay, so I've got 3 exhibits here, all hinting around the same type of idea for infinity. I'm going to tie it together for you here. One, with finite sets, those obvious facts that we had are not so obvious anymore. A proper subset of an infinite set may not be smaller than the set. It may be exactly the same size. It may be exactly the same cardinality. Now, working with finite things, we're under this impression that if you take something away, you make it less. And that's not true with infinity. If you take something away from infinity, you may still have infinity, or you may have 7. Right? But it doesn't work the same as the way that it works for finite sets. And there are just as many multiples as 5 as there are counting numbers. Subtraction and division with infinity aren't undefined, they're ill-defined. They're over-defined. Your math teachers will tell you, you can do infinity plus infinity, and you can do infinity times infinity, but you can't do infinity minus infinity. To that I say, ha! Sometimes you can. But don't say that to your teachers, because they give you points. All right. The mind-boggling fact here for me is this idea that the things that happen with finite mathematics and the things that happen with infinite mathematics change dramatically and aren't always immediately obvious. It's not always intuitive that something has changed when we've transferred from the finite to the infinite. And it means, as mathematicians, as scientists, we need to be careful when we deal with the infinite, because the things we think we may find oftentimes are completely different and beyond what we might even imagine or intuit. So, and the concepts we use to understand numbers, the counting numbers, don't work with infinity. The implication of that is infinity cannot be a number. Infinity must not be a number. Infinity breaks mathematics, but if infinity were a number, mathematics would fail completely. So these are my mind-boggling takeaways for infinity, and I think now it's your turn.
Understand infinity on a mathematical level. And there may be surprising things, many shocking things, many bizarre and disturbing and wonderful and amazing things about infinity. But I think the most wonderful, the most important, the most surprising, the most shocking is that there are different levels of infinity. There are different infinities that we can use in different cases. Now I gotta throw this guy's picture up here because this is wonderful. Most of the foundational ideas of mathematics we're talking about tonight were from this fine gentleman. This is Georg Cantor. He was a German mathematician who really worked all this out. Before him, people talked about infinity and then kind of thought of it as this kind of vague, ethereal, out there sort of concept. Not something we could really do something seriously mathematical with. And he showed how we can wrestle with infinity, how we can tame infinity in certain circumstances. And one of the central ideas, as my estimable colleague has been talking about, is that we can compare infinities by seeing if we can come up with a one-to-one correspondence. If I've got an infinite list of things over here, and another infinite list of things over here, and I can match them up, so that for everything on this list, it corresponds to exactly one thing on that list, for every one thing on this list, it corresponds to exactly one thing on this list, and my matching covers everything over here, and everything over here, and nothing's left over on either side, then I would say these infinities are equal to each other. So this is wonderful, and we can use this to compare different infinities with each other. We can compare the infinity of the numbers from 0 to 1 with those from 1 to 2, and we can make a matching, so that's the same level of infinity. Or I could compare all the infinity of the counting numbers, 1, 2, 3, 4, 5, etc., with the infinity of just the even numbers, 2, 4, 6, 8, 10, 12. And it seems like, well, you should have only half as many of even numbers as all the numbers, but I can make a one-to-one correspondence between them. 1 could correspond to 2, 2 corresponds to 4, 3 corresponds to 6. For every number on this list, it corresponds to exactly one number on that list. There's nothing left over on either side. And we find that we have equal infinities. That's wonderful, and that's amazing, and that's incredible. And the interesting thing is, we can find infinities that are different, that are bigger. We can find infinities where you cannot line them up. You can't create a correspondence to each other. We want to make a larger infinity than this. So Cantor used this symbol. It was they used all the letters in the Greek alphabet, so he used that as a letter out of the Hebrew alphabet. He called it Aleph No, and he said that's the infinity of the counting numbers. 1, 2, 3, 4, 5, 6, etc. The infinity of all those numbers, and he started comparing things back and forth. And for a while, it appeared that infinity was infinity, right? That there was one level of infinity, and that's all there was. But let's compare the infinity of the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, with the infinity of all the real numbers. So all the real numbers include all possible decimals, with every number of decimal places you could ever have, including, something like a third would be 0.33333 forever, that's fine. But this would also include irrational numbers, those where they have the decimal places that go on forever and they never repeat themselves and they just keep going and you can never calculate the last decimal place of them because they keep going. Like pi. Pi is everybody's favorite irrational number, 3.1415, and it just keeps going. And there's always more decimal places and you never run out of it. And there are other numbers like this. The square root of 2 is another very popular irrational number. There's an infinite number of decimal places. You never run out of them. You could never finish writing down all the numbers in the square root of 2. E is another popular. It's an irrational number. And I want to consider the infinities of all possible numbers, including both the rational ones and then all these irrational ones too. So including all numbers with numbers of decimal places that just go on forever and never settle down, and there's no simple repeating pattern to it or anything like this. I want to compare the infinity of those, the real numbers, all possible decimals, with the infinity of all of the counting numbers, 1, 2, 3, 4, 5. And so what we can do is we want to see if they are just the same level of infinity. So, well, we can try to create a matching between them. I can try to create a relationship between them. And I can't. But just because I can't think of how to do it doesn't necessarily mean it's impossible to do. Just because I can't come up with this. So I can spend my whole life trying to come up with ways to match up all the real numbers, all this with the counting numbers. And just because I can't figure out how to make it happen, that doesn't necessarily mean that somebody else, somebody smarter than me, will come along eventually and figure out how to do that. But that's what I need to do. In order to logically prove, in order to mathematically prove that this is a larger level of infinity, a bigger level of infinity than the counting numbers, the Aleph No, the 1, 2, 3, 4, 5, 6, 7, that's what I would have to do. And Cantor came up with a really, really clever way to do this. So there's the question. Is a one-to-one correspondence possible? I have two infinities. I want to compare them. I've got the counting numbers over here. I've got the real numbers, all possible decimals over here. I want to know whether it's possible to come up with a one-to-one correspondence. So here's the clever way we're going to do this. We're going to assume that there's some way to do it. I don't know the details, but somebody has figured out a way to do this, to list out, to create an infinitely long list that includes all possible decimal numbers on it. And then I'm going to assume that exists. And then I'm going to show that that leads us to a contradiction, that I can actually create a number which is not on this list. So in order to have the same level of infinity, I have to be able to create this one-to-one matching correspondence. So over there on the left, I got my list of the counting numbers. 1, 2, 3, 4, 5, 6, etc. I'm hiding a lot under etc. And then over on the right, suppose there's some really clever way, some genius has figured out some way to figure out a way to list all possible decimal numbers over here on the right, and has done it in some clever way that whatever your decimal number, it's gonna be on this list somewhere. And maybe it's the millionth number on the list, or maybe it's the 2,394,517th number on the list. But assume that somebody has figured out some way to do this. So in this example, suppose number 1 on the list is this one, 2.397204817, et cetera, et cetera. There's a whole bunch, there's an infinite number of decimal places behind that. And then the second number on the list is this one, and the third number on the list is this one. And so if these are the same level of infinity, somebody somewhere should eventually be able to come up with a one-to-one correspondence, a one-to-one matching between the numbers over here on this list and the numbers over there on that list. And what we're going to do is we're going to show you that this is not possible. That no matter what list you come up with, that even an infinitely long list, there will always be real numbers. There will always be decimal numbers that cannot possibly be on the list. And here's how we do it. Oh, this is fun. Here's how we do it. In order for two decimal numbers to be equal to each other, they must be equal in every single one of their digits. They got to be equal in the tens place, and the hundreds place, and the thousands place, and the 10,000th place, and every single one of their things to be equal. So I'm going to create a number which is not going to be on my list. So we imagine somebody's come up with this list. It's an infinitely long list, and I'm going to imagine that this person has claimed that every decimal number there exists is on this list somewhere, at some point. And maybe you got to go a long way down to it. But I'm going to say, no, I can create a number which is not on your list. And here's how I do it. I have an infinite number of decimal places to work with. So I'm going to take the first number on the list, and I'm going to look at the tens place. And let's see, in this one, my first number in the tens place, it's 2.39, so in the tens place, it's a 3. So all I need to do to make sure it's not that number is I'm going to just choose something else, anything other than 3. A number different than 3 is 6. So down here at the bottom, I'm going to create my number, which is not that. And it's going to be not any of the numbers on the list. And so I know it's not going to be the first number on the list because it's not going to have a 3 in the tens place. I'll make it be 6. And then, second number on the list, well, I go to the next decimal place, and I'm going to say, I know my number isn't going to be that one, because in the next decimal place, in the hundreds place, let's see, this number in the hundreds place has a 2. There are 10 digits. All I got to choose is something other than that one. So this one has a 2 in it. I'm going to make that one be, I don't know, an 8. Just any of the other 9 digits, and I know it's not the second number on the list. And then let's see, the third number on the list, there we get the tens, hundreds, the thousands place. That has an 8. All I got to do is choose a different digit than that. If we assume that there is somebody somehow has cleverly created some way of systematically listing out in an infinitely long list all possible decimal numbers, I can always create a number which is not on that list. It must have been left over, which could not be part of this one-to-one correspondence. Because in order for two decimal numbers to be the same number, they have to be equal in every single one of their decimal places. And I've got an infinite number of digits to play with. And so I use the tens place to say that my number is definitely not the first number on the list because it's going to have a different number in the tens place. And it's definitely not the second number in the list because it's going to have a different number in the hundreds place. And it's definitely not the third number on the list because it's going to have a different number in the thousands place. And I can work my way down. Since I have an infinite number of digits to work with, then I can assure that the number I'm creating is not any one of the numbers on this list, even though the list is infinitely long. Even though it's got an infinite number of numbers on it, all the way down, I can create a number which is not on that list. And what that means is that there's more than one level of infinity. That the infinity of the real numbers, the infinity of all possible decimals, including all those crazy irrationals, that infinity is a larger infinity. Then this argument means that no matter how you list them out, even if someone really clever comes up and tries to come up with some way of matching up every possible decimal with every possible counting number, no matter how you do this, I will always be able to create at least another number on the list. It's not the first number on the list because it differs in the tens place and in the hundreds place and the thousands place. And so it cannot be found anywhere on the list at all. And so we can always create a number which is not on this list, even though the list is infinitely long. And because of that means there's more than one level of infinity. The infinity of all possible real numbers is a bigger infinity than the infinity of all the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. As a matter of fact, I could even limit my real numbers to the interval just between 0 and 1. I don't even need to use the tens or hundreds places or anything like that. I can deal with things that are just purely decimals, purely numbers between 0 and 1. And I can make exactly the same argument. I can make it different in the tens place, in the hundreds place, in the thousands place. And I can therefore show that the number of decimals, the number of real numbers between 0 and 1 is infinitely larger than the number of counting numbers, the 1, 2, 3, 4, 5, 6, because there's no way of creating a one-to-one correspondence. Anytime anyone who says they can do that, I can always create another number which is not on the list. That's amazing. That's just mind-meltingly awesome. The fact that we can have a different level of infinity, which is even bigger than that. So we typically call this infinity the continuum infinity, and we need this. We need this to understand the universe around us, because we need this in order to describe the location of things, in order to measure time and space. If I want to measure things like how things move and trajectories of objects, and I want to use Einstein's equations to measure how gravity influences the universe, I need real numbers to describe all the positions between here and there. This is not only something that's wonderful and amazing and incredible, but it's also useful in order to describe how our universe works. We use real numbers all the time. We transcend infinity every time we move, every time I walk around the room, every time I walk from here to there. There's a continuum infinity of places between here and there. If our theories of space and time are right, we're transcending that continuum infinity every time we move. And that's absolutely amazing. When this came out, when this was published by Cantor, lots of mathematicians and philosophers and people thought that this was absolutely, that this was ludicrous, that you could do math with infinity and what you can compare these things. I love this. There's a great mathematician, Leopold Kronecker. He as a result of this, he called him a scientific charlatan. You know, he's just tricking people, swindling them with this goofy idea that you can compare infinities by creating these one-to-one matching. The philosopher Ludwig Wittgenstein read his proof, and he called it utter nonsense. That, couldn't believe anybody even believed that. But in 100 years or so since then, his work survived the test of time. It's inspired mathematicians to explore other sorts of things, to realize that the limits of what we can study mathematically are only limited by our own creativity, by our own imagination, by creating a logical, reasonable way of comparing two different levels of infinity. Cantor opened up the possibility. It's a whole field of mathematics, transfinite arithmetic, comparing different levels of infinity, trying to figure out all these relationships. This is a wonderful, beautiful, extraordinary area of mathematical exploration and discovery. Thousands of people have spent their careers and published papers and all sorts of wonderful things exploring this. I love this one. David Hilbert, he's the guy at the bottom here. He said, hey, even though there's all this criticism and all of this, he thought it was just so wonderful what Cantor had discovered. He said, no one shall expel us from the paradise that Cantor has created. I think that's wonderful. I think that's amazing. The fact that we can compare infinities with each other and that there are different levels of infinity. After this, Cantor went on and made an even more beautiful, more intricate proof, which I'm not going to go through the details of, where he proved that not only is there at least two levels of infinity, because Aleph, no, 1, 2, 3, 4, 5 infinity, and then a continuum infinity, he was able to logically prove that there is an infinite number of levels of infinity. No matter what level of infinity you have, he proved that he could create an even larger one. And so not only is infinity big, but there's an infinite number of infinities, each infinity larger than the previous one. That is the most wonderful and amazing and incredible discovery about infinity. Thank you.
infinity. It's not the one.
Very good. And that's what everyone would have agreed that up until Cantor, up until the and how could you even logically do that? What would be the process? And what Cantor gives us is a logical, consistent, reasonable way to compare infinities with each other. We can create this one-to-one matching from one infinite list to another infinite list, nothing left over on either side. That is a
That
definition of
assumes an ending.
It doesn't. It doesn't. And that's the beautiful part about it. If we go back to the analogy that I bought, the red and white yellows, right? Like if I have an infinite number of Legos, I don't need an ending if I'm just matching them up. And the argument that the mathematicians make, the argument that Cantor made, was I don't need to see the process all the way through. I just need a set of instructions of how it would be done. And that set of instructions is what Dr. Cline talks about, is of these infinite lists of pairing them up, right? So I don't need to know, I don't need to be able to count infinitely many long in order to know how to find the next number.
Right, the counting is an oxymoron.
Correct. But let's start with this. If we assume the existence of numbers, not even numbers, we assume the existence of the number 1. And we assume that from the number 1, or from any number, 1 being the only number so far, I can add 1 to it and get another number. Now I've got a recipe for making numbers. So now not only is 1 a number, but its immediate successor 2 is a number. And its immediate successor 3 is another number. And I've got a recipe for creating those numbers, even though I haven't created any of them. Even though I've just assumed that 1 exists and I'm adding 1 to it. Now, under that framework, we can argue that if we define infinity as something that's bigger than every number, well then certainly I can add 1. And the statement infinity is bigger than that is true axiomatically, by the assumption that there's something beyond. Now, if we acknowledge that there's something beyond, then the one-to-one correspondence thing follows directly. We don't have to assume an ending of anything. Does that make sense?
There's ending no ending, that's all.
Sure.
That's the truth.
See if we've got some more questions. I see a hand back up here.
So with 0.9 repeating, so 9 is at infinitum, is 0.9 repeating equal to 1 then? Because, like, logically, if you go 8/9, and it's 8 at infinitum, and so 9/9 must be 9 at infinitum, but it's also equal to 1. So 0.9 repeating equals to 1.
0.9 repeating is equal to 1. And I think one of the things that causes a lot of uncertainty with that is this assumption that numbers can only be represented one way. A decimal representation of a number is a convenience. But it doesn't mean that the decimal representation of a number is unique. The number 1 has several different representations. One of them is the number 1. One of them is as an infinite series of 9/10 plus 9/100 plus 9/1000. So yes, those are the same numbers. No, that's not a contradiction. It just exposes a flaw in our representation of the numbers, not the numbers themselves.
Who else has a question?
Wait, that corner. Jackson.
All right, so I'm thinking in terms of, deciding who wins this debate, right? So you told us that it's possible that infinity minus infinity can equal 7. So that, if I'm understanding correctly, that's implying that the first infinity is 7 whole numbers bigger than the second infinity, right?
No.
Elaborate on that.
So, by definition, infinity is a construct that satisfies the relationship infinity is greater than any real number. Okay. That's not exclusive from doing arithmetic with infinities. And doing arithmetic with infinities means we need to be paying careful attention to what order things happen in. If I rearrange things in a particular order, I can get a different result, even though I have the same number of things, even though those things have the same cardinality, right? So part of the challenge about infinity And I think Dr. Cline approached this exactly. Part of the challenge about infinity is that we assume infinity is a singular. And infinity is not a singular. Infinities are several things. And when we deal with them, we have to deal with them differently. Now, if it were two real numbers, if I have two real numbers and their difference is 7, that's equivalent to saying that one number is 7 bigger than the other. If I have two infinities and their difference is 7, that's not equivalent to saying one infinity is bigger than the other. They're actually the same thing, presenting themselves slightly different.
You said there was proof that we can make infinite infinities bigger than the previous one. Does that mean for any infinity, you can find an infinity that's smaller than that one?
Not necessarily. That's a more complex question. Whether we can always have an infinity which is smaller than a given infinity is, that requires a little bit more time than we have to discuss. That's a difficult question to answer.
Perfect. So infinity is super cool if I plan to get a PhD in mathematics. But are there any like real world implications of theories on infinity that are like useful for the average?
All right. One of the ideas that comes out of infinity is infinity allows us to do calculus. And in calculus, allows us to study things that very smoothly. If I want to study the trajectory of a stone that I throw, or I study the orbit of an asteroid around the sun, well, as the asteroid orbits around the sun, what do I find? I find that at every point in time, gravity's constantly change direction, just a little bit. At every instant in time, it has a very slightly different trajectory, because in order to move in any curving path, at every instant, something must constantly be changing direction and speed. Its velocity must be changing. We must deal with infinity every time we deal with anything that curves. And there are lots of things that curve, absolutely. Whether I'm trying to map the trajectory of a space probe that I'm trying to send out there to visit the planet Mars, whether I'm an engineer trying to measure the forces as they vary on a steel beam, and the forces change smoothly from here to there, and there's an infinite number of points along that beam that I'm going to model, and so I need to see how these things change. Anytime we're doing calculus, anytime we're dealing with anything that curves, anything we're dealing with anything that varies smoothly from one place to another, we have to deal with infinity.
Question for US system. So you mentioned, right, like on that sort of list of three decimal values. Add one more. So if you never address the other list, couldn't you always just add one more value to that one?
One thing I know about the list of the natural numbers, the counting numbers, is I know what order they count. There's a 1, and then after it there's 2, and I'm pretty sure after that is 3, and then usually after that comes 4. And so there's a very specific listing to that. The natural numbers have an order to them. A clear, definitive order wherever you are, and there's no end to the list. I mean, whether I get to 1 million, there's 1,000,001. I get to 1 billion, there's 1,000,001. But there's a clear ordering to that. So if I imagine that someone could come up with some way of matching every single one of those with every one of the real numbers, the decimal numbers, then, well, okay, if I imagine this listing exists, that means, that would have to mean that for every one of these, there's one of those, and for one of those, there's one of these. That means I've already used up all of them, even though there's an infinite number of them. Every single one of those already corresponds to a particular decimal. So that means you tell me a natural number, you tell me 9,436,517, and then if it was possible to come up with this list, I could go to my list and say, oh, that corresponds to the number 0.2653, and then I would have some infinite number of decimal points that were after that. So if I imagine that such a list already exists, somebody has set it up, some really clever, smart, genius person has come up with that list. And for every one of these, it already corresponds to a specific decimal number over here. If I can now create a new decimal number, which is not the first one, or the second one, or the third one, or any specific one on the list, well, then I've broken the list. And then I've shown that I have some number that no matter what it is, it doesn't, if these are already used up corresponding to those, I can always create some number which isn't any one of those.
Doesn't that mean inversely though, that if you have all of your decimal values used up, so to say, and then you added one to your infinity on the other side, that then you would have to add another decimal value so that it would happen there. So you could add an infinite number of decimal values, but then inversely, you're also able to add an infinite number of counting numbers. So
The idea, I've already used up all the counting numbers, every single one. They already correspond to all of these decimal numbers. And so I'm imagining that this list is an infinitely long list, but it's a book I can look through. It's a function. It's a mathematical process that I can go to take me from this number to that number. And if I can show you that there's a number over here which doesn't correspond to any one of those, it means the matching is broken. It means the matching is
Two more questions. From here.
So this is slightly off topic of insanity, but during the first presentation, during the analogy of the dragons, you're talking about how the dragon's taking their earliest prime factor, and you said that you'll never run out of primes. Correct me if I'm wrong, but there's no formula for prime numbers. So how would you prove that you would never run out of primes? Can you prove that primes don't stop at some arbitrary point?
I can.
You might want to be a math major. There's a class called discrete math. We proved that. Where are my discrete math students? Oh, yeah. I want to prove that. Take the class.
It's an excellent question. It's one that take one. Yes.
All right, one more question. Back to over there.
Can you perform operations between different sizes of infinity?
So, like, can I personally? So here's the thing. When we talk about infinities, this is natural. When we talk about infinities, there are typically different ways we talk about them. One of the ways we talk about them is arithmetically in terms of how they interact with numbers. So when we're looking at the real number line, if I have the real number line, draw it out, I have a zero somewhere in the middle, and I point both ways, and I say infinity's that way, negative infinity's that way, or whatever, right? That's one way I might talk about infinity, comparing it to numbers. Another way we might talk about infinity is in terms of the size or the cardinality of sets. So we use the word infinity to say there are infinitely many counting numbers, and there are infinitely many integers, and there are infinitely many real numbers. When we're comparing the size of sets, typically we're not doing arithmetic operations on those sizes. We're just comparing. So to my knowledge, no, it's not something that's typically done. Doing arithmetical operations between different sizes of infinity. I'm not sure about that. So clearly, Dr. Cline can't answer that question.
awesome. And the vote is so close. It is so close. But the winner is Dr. Wendt.
Thank you all for coming. This is awesome. We're hoping to remind this Wednesday, make it a semesterly thing. Make sure your high school students get plenty of extra credit. There's college students actually have to pay points to come here. So they can hit on their grade for this. Also,
And for my other students, some of this is on the test tomorrow.
all right, and we gotta put the plug out there. If you are a high school student who's still considering where to do your studies, if you're looking at something within the Department of Everything, that's math, computer, computer science, computer information systems, computer information systems, physics, or anything tangentially related, and everything is tangentially related to mathematics, give us a look. We got a lot of stuff. We'd love to talk with you. You can contact me through our website. I think you can like and subscribe to our YouTube page.
There are also some specific scholarships for Montana local students like
Absolutely.
Carroll. So,
All right, thank you all for coming.